You've probably rented a U-Haul at least once. Maybe you were moving apartments, hauling furniture, or picking up something that would not fit in your car. And the moment you settled into the driver's seat, something felt immediately off. The steering wheel was enormous, a wide, thick ring sitting almost against your chest, big enough to feel like it belonged in a different machine entirely. You assumed it was because everything on a truck is bigger. Big mirrors, big seats, big wheel. Obvious. That assumption is wrong. The size of a truck's steering wheel isn't tradition, and it isn't proportion. It traces back to a specific physics problem that engineers discovered the hard way, a problem involving forces most people never think about, a federal law that requires trucks to remain controllable even when their systems fail, and a principle that has been quietly running in everything from ocean vessels to farm equipment to the machines that built the interstate you drove to get to that rental lot. By the end of this video, you'll understand exactly why that wheel is the size it is, and you'll never look at the driver's seat of a large vehicle the same way again. Let's start with what everyone gets wrong. The first answer most people land on is correct. A bigger steering wheel means more leverage, which means less effort to turn. This is basic physics, the same principle as a long wrench loosening a bolt that a short wrench cannot budge. The mathematical relationship is simple. Torque equals force multiplied by radius. Double the radius of the wheel, and you produce the same turning force with half the hand pressure. This is not an engineering insight. It is a lever. Archimedes figured it out. So yes, a 20-inch truck steering wheel generates roughly twice the steering torque at the steering column as a 10-inch car wheel, using the same hand force from the driver. A standard passenger car steering wheel runs about 14 to 15 inches in diameter. The steering wheel on a Class 8 semi-truck is typically 18 to 22 inches. Some older configurations ran even larger. The leverage difference is real, and it matters. But here's the question the answer does not close. If leverage is all this is, why does a truck need so much more mechanical advantage than a car? A car uses a 14-inch wheel and works fine. Why cannot a truck use something similar and call it solved? What is the truck fighting at the front axle that a passenger car simply is not? The lever answer tells you the mechanism, but it does not tell you what the mechanism is fighting. And what it is fighting is something most people have never thought about in connection with a steering wheel. That number is what changes everything, and it's a lot bigger than you would guess. Here's what the steering system on a loaded semi-truck is actually working against every time a driver turns that wheel. A fully loaded Class 8 semi-truck places up to 12,000 pounds on the two front steer tires. The federal legal limit on a steer axle is 20,000 pounds on U.S. interstate highways, and most trucks run between 10,000 and 12,000 under real-world load conditions. Compare that to the front axle of a typical passenger car, which carries somewhere between 800 and 1,200 pounds. Now here's the part that makes the steering wheel make sense. The steering system is not turning the wheel in the air, it is overcoming the friction from thousands of pounds of iron pressing down through the steering knuckle and into the pavement at the contact patch. At highway speed, aerodynamic forces and gyroscopic momentum help relieve some of that load. But in a parking lot, a rest stop, a loading dock, anywhere the truck is moving slowly or stopped, the driver is working almost entirely against that static friction, against the dead weight of 10,000 or more pounds pressing down through the front axle. That's the real enemy of the steering system. Not the truck's size, its weight, concentrated on two front tires at low speed with no physics helping. And this is where the obvious answer, just use power steering, runs into a problem. Hydraulic power steering does handle most of that force. It was invented precisely because trucks needed it. But here is what that explanation misses. Power steering can fail. And what the law requires to happen when it does, on a vehicle with 12,000 pounds on the front axle, is the real reason that wheel never got smaller. Here is where it gets genuinely strange. Federal Motor Vehicle Safety Standard 204 requires that any commercial vehicle remain steerable after a power assist failure. This is not a guideline or a best practice. It is a legal mandate. This is not hypothetical. It is the law. If the hydraulic power steering pump fails, the driver must still be able to control the vehicle. On a passenger car, this is uncomfortable but manageable. A car's front axle carries roughly 1,000 pounds. Most adults can steer a car with failed power steering, with effort. On a Class 8 truck with 12,000 pounds on the steer axle, steering without hydraulic assist is a different category of physical problem entirely. The forces involved require every available mechanical advantage the driver can access, and that mechanical advantage comes from the large diameter steering wheel, not as the primary control interface, because the power steering handles that, as the backup. The last line. The reason the truck does not become uncontrollable if the assist system fails at highway speed. The wheel stayed large because the failure condition demands it. This dynamic predates the federal standard. Before hydraulic power steering became widespread on commercial trucks, it was gradually adopted through the 1960s and the 1970s as the interstate highway system created longer, more demanding routes, and drivers managed entirely on mechanical advantage. Fleet mechanics from that era documented severe hand and arm fatigue as occupational conditions, steering kickback when a front tire hit road debris and the energy traveled back through the column into the wheel, snapping it violently in the driver's hands, was a documented cause of accidents and injuries. The large wheel was the only available tool to manage forces that were simply beyond what a smaller diameter could handle without destroying driver endurance over an 11-hour day. Power steering made the primary task manageable. It didn't change what happens when it fails. But this still leaves something unanswered. Why did the large wheel appear in the first place, long before the modern loaded semi, long before power steering, long before the interstate? The same design principle appears in places that have nothing to do with trucks at all, and understanding where else it exists is the part that makes the whole picture click into place. Here is the pattern. Any machine that requires a human operator to mechanically overcome the resistance of heavy loads at low speed without sufficient power assist, or with the requirement that power assist failure must remain survivable, ends up with a large diameter control interface, every time. Without exception. Ship helm wheels on traditional ocean vessels reached 4 to 6 feet in diameter, not because ships are large, but because the water pressure on a rudder at sea is enormous, and before hydraulic or electronic steering assist existed, the helm wheel was the entire solution. The physics demanded the diameter. Farm tractors run steering wheels in the 18 to 22-inch range, nearly identical to a semi-truck, because tractors carry heavy front axle loads and operate at low field speeds where momentum provides no help. The contact friction problem is the same problem. The lever solution is the same solution. Early aircraft used large control yokes for the same reason. Control surface forces before hydraulic flight control systems required mechanical advantage that only large diameter inputs could provide. As hydraulic and electronic assist improved, yoke sizes shrank. As car power steering improved, car steering wheels shrank from the large diameter designs of American automobiles in the 1950s, down to the compact wheels in modern vehicles. Industrial forklifts, cranes, port equipment, every machine where the operator must overcome heavy loads through a manual or semi-manual interface ends up with large control diameter. The truck steering wheel is the same solution, applied to the same physics, across 2 centuries and a dozen industries. You have been driving past this answer your entire life, and you did not quite have all of it yet. So here's where you actually land after all of this. You started with a U-Haul steering wheel that felt wrong. Too large, too close, too much wheel for an ordinary person. You assumed it was proportion. Then you learned it was leverage. Torque equals force times radius. Then you learned what the lever was fighting. up to 12,000 pounds, pressing down on two front tires, resisting every turn at low speed. Then you learned that the wheel stayed large even after hydraulic power steering arrived, because federal law requires a loaded commercial vehicle to remain steerable when power assist fails. And then you saw the same physics appear in ship helms, tractor steering, and early aircraft controls in every machine where heavy loads and the requirement of manual survivability have ever met. That steering wheel isn't big because the truck is big. It's big because the forces on a loaded steer axle are genuinely immense, because power steering failure at 12,000 pounds is a survivable condition only if there's enough mechanical leverage remaining. And because that large diameter ring is the physical embodiment of every engineering lesson learned before hydraulic assist existed to make it easier. Next time you sit down behind the wheel of a moving truck, you'll know exactly what you're holding. Not just a steering wheel, a lever, a backup safety system, and a solution that has been solving the same problem in the same way for as long as humans have tried to steer heavy things. You'll be the only one in the cab who knows that. And if you think the steering system is interesting, wait until we get into what's actually happening inside those front axles and why the kingpin design that makes all of this possible hasn't fundamentally changed in nearly a century.